Hello, my name is Benjamin Zhao, and welcome to the talk titled Not One But Many Tradeoffs: Privacy versus Utility in Differentially Private Machine Learning. As I said, I'm Benjamin. This was work done in conjunction with Dali Kafar and Nicholas Cortelis, and we're from UNSW, Macquarie University, and Telefonica Research. Now, why are we here? Data holders have been pushed by their own good conscience and various laws such as COPPA, GDPR, e-privacy, and CCPA to protect the data of their users. And data holders can protect their users with a plethora of privacy-preserving techniques constantly being proposed. However, selecting the right one to use can be a tricky task because these data holders still want to maximize how well their models perform. Or in other words, they want to make sure that their models still make good predictions. And as we know, these two goals are at odds with each other. With increased privacy, the amount of information we can distill from each individual sample is less. And that makes utility, or our ability to generalize and learn a particular rule, much harder. And that's where this study comes in. We want to find the optimal trade-off between privacy and utility. And finding this optimal trade-off is hard. Now, before we get into answering that question, let's go through a little background to help us here. First, differential privacy. I've mentioned it already, but what exactly is it? It can be described as mathematically guaranteed plausible deniability for a given data point. Or more specifically, if you have two datasets that differ by one data point, you should not be able to tell the difference between those two up to a certain limit. In this work, we look at two specific machine learning algorithms, neural networks and naive Bayes. Now, when we refer to utility, we refer to accuracy loss, the difference in prediction accuracy of our differentially private machine learning model when compared to a non-private baseline model. And whilst privacy is captured within the limits set by differential privacy, we also want to capture the real-world privacy leakage as measured through two privacy attacks. Membership inference, which is knowledge of whether or not a given vector was used in the training dataset of the model, and attribute inference, where given a partial vector missing a few attributes, can we use the model to recover what those missing attributes are?
Now, machine learning models can be made differentially private by injecting differentially private noise. Now, where that noise can be injected can occur in three distinct stages. Stage 1 occurs whilst the data is being collected or before the learning has even begun. And that means it doesn't actually care what machine learning technique is being used. It's model independent.
Stage 2 is where the noise is injected whilst the machine learning model is learning. Finally, stage 3 is after the model has completed learning. Now, that's when you add noise directly on those learned parameters. And as I said before, we're focusing on neural networks and naive Bayes. Now, fortunately for us, as stage 1 was model independent, both neural networks and naive Bayes can be made differentially private by injecting noise in stage 1. Neural networks, it undergoes stochastic gradient descent in order to update its parameters. We can inject differentially private noise on those gradients. And naive Bayes learns the probabilistic distributions of the output classes as informed by those input values. Adding noise directly on those probabilistic distributions ensures it's differentially private.
And to actually measure the utility and privacy, we will be using an accuracy loss, a membership inference attack, and an attribute inference attack. Our original trade-off question can be particularly difficult to answer, as with new differentially private technique proposals, they often compare themselves to similar techniques and not compare themselves to the wider landscape of tools.
Now, to give more details about our specific procedure, in regards to the training dataset, we use 4 different datasets. We use a synthetic dataset from which we generate samples and cluster into different numbers of classes. We use the purchase dataset, we use the CIFAR dataset, and we use the Netflix ratings dataset. You can find more details about these various datasets in the paper. As for differential privacy, we are focusing only on epsilon differential privacy, where epsilon is our privacy budget. We vary epsilon between 0.01 in orders of 10 all the way up to epsilon equals to 1000. We also check the halfway point of each of those steps. We've discussed accuracy loss as the difference in prediction accuracy between private and a unprivate model. But the specific membership inference attack we use is Salem et al. From MLleaks, which uses the maximum confidence in order to determine membership inference. For attribute inference, we use Yom et al.'s realization, whereby the permutations of all missing attribute permutations are used to determine the correct missing attributes. With each configuration of dataset, variable epsilon or privacy budget, and differentially private machine learning method, we repeat that specific configuration 10 times to ensure spurious runs do not skew our results. Now let's dive into some results. So on the left here, you have naive Bayes when differentially private noise was applied on stage 1. And on the right hand side, we have naive Bayes when differentially private noise was applied on stage 3. And this is for real world data, but we've aggregated our results together from those various datasets depending on the number of classes. Both these plots show accuracy loss, which is our measure of utility. Accuracy loss is bad when it's 1, it means you've lost all of your accuracy. And when it's 0, it means you have lost next to no accuracy when compared to our baseline. Now, from the handy red lines I've drawn here, the solid red lines represent a fixed privacy budget in both of these situations. Now, if we track across on the dashed red line, we can see that when the noise is applied later in the pipeline, that's stage 3 versus stage 1, we get better preservation of the prediction accuracy. Or in other words, the accuracy loss is closer to 0, meaning we haven't lost any accuracy. And this is consistent throughout the differentially private machine learning techniques we look at. One interesting thing to point out on these plots is that in stage 3 naive Bayes, that accuracy loss actually drops into the negative. And what that means is the prediction accuracy has actually gone up. And we believe that's because a little bit of differentially private noise has actually assisted the generalization of that model. Moving on to privacy leakage, specifically membership inference on real-world data. One thing I'll immediately point out is on the vertical axis, we're looking at advantage. Now, I won't go in depth into advantage, but it only considers the advantage gained by having that particular vector within the training dataset versus not having it in the training dataset. And again, with the red lines, we can see that larger reductions in privacy leakage is achieved with less noise when it is applied in early stages. Changing pace now and looking at the privacy leakage of attribute inference on synthetic datasets, we can very clearly see that in the red rectangles, the inflection point of the privacy attack does not directly depend on the noise. Instead, it's dependent on the differentially private machine learning method and the stage in which the noise was applied. And I mean for both membership and attribute inference attacks. Now, with the membership inference plots next to the attribute inference plots, we can see that those rectangular boxes, or the inflection points, happen at basically the same value of epsilon. And those differences largely correspond to just the differentially private machine learning methods. Now, so far, we've only been looking at accuracy and privacy by themselves. So let's change pace here and actually compare them side by side. So switching out those attribute inference plots for the ACL, or the accuracy loss, we can see that those red rectangles essentially don't move. And we can see that the inflection point of both the attacks and the ACL roughly correspond to the same differentially private noise. So to quickly summarize what we've talked about, we've observed that for a given amount of noise, if applied later in the machine learning pipeline, prediction accuracy is preserved better. Larger reductions in privacy leakage is achieved when less noise is applied in those earlier stages. Third, the inflection points of those privacy attacks do not directly depend on the amount of DP noise applied. Instead, they correspond more to the actual DPML method and stage of the applied noise that was used in that config. And four, the inflection point of the attacks and the accuracy loss roughly correspond to the same amount of differentially private noise for a given method and stage. Now, continuing, we have dealt with both synthetic and real-world data, but now let's directly compare them and their class complexities. Looking at these two figures here, we've got synthetic data on the left-hand side and real-world data on the right-hand side. Both of these are for stage 3 naive Bayes and accuracy loss. Now, we can see that between the synthetic dataset and the real-world dataset, they look pretty similar. And if I mark out the red circles here, we can see that the data complexity, or the number of classes in a given dataset, is actually unlikely to influence the position of the inflection point. You can see all those lines, they sort of bend away at similar points. And again, there are similarities in the trade-off between the synthetic and real-world datasets. And it's particularly interesting as this similarity would allow us to take a synthetic dataset and estimate the optimal trade-off point for a given differentially private machine learning technique without having to look at a potentially private dataset. Now let's switch our setting a bit. We were looking at a general any accuracy loss, any epsilon value. But what if we had a constrained requirement on utility, a constrained accuracy loss, meaning we cannot exceed that particular value? What is the best privacy that I can achieve? We can see from the top table that stage 3 differentially private naive Bayes absolutely dominates the table, consistently offering the highest privacy guarantee when compared to those other differentially private methods. When we have a constrained privacy guarantee, meaning we have to offer at least this much privacy, we can see again, stage 3 naive Bayes consistently offers the lowest ACL for those more relaxed guarantees. However, we do see stage 1 neural networks offering lower ACLs when a strong privacy guarantee is needed. Although we will note that that accuracy has already degraded quite significantly. Thus, to answer the question of which technique is the best, from our test here, I can confidently say that stage 3 naive Bayes would serve our utility and privacy purposes the best. To summarize again, we saw that the data complexity is unlikely to influence the position of the inflection point, and that there are similarities in the trade-offs between both synthetic and real datasets that may be exploited to estimate the optimal trade-off position without actually looking at the dataset. We would also recommend stage 3 differentially private naive Bayes for both accuracy and privacy constraints. In terms of future directions and what we've done since this work came out, we hope to incorporate some additional differentially private machine learning approaches, whether that be logistic regression or random forest, or just looking at alternative differentially private machine learning methods for some of those configurations we talked about earlier. There are other alternative membership and attribute inference attacks that may be used here. This has largely been an empirical study, so we may potentially predict where that inflection point occurs, either through generic benchmarks or by modeling that privacy-utility relationship. Finally, we've focused on utility as measured by accuracy loss, or how well a prediction is made. There are other alternative utility measures that may be relevant for a model holder. For example, that may be how many resources this model consumes whilst training or predicting, or perhaps the fairness of those predictions. Nevertheless, there's many exciting avenues for this research to progress, But I would like to thank you for listening to this talk. Additional details and code can be found in our paper. This QR code will take you there. And again, thank you for your time. And are there any questions?